Okay, so mass out of spring. Decompress length of 10 centimeters. Okay. So forgive me for to pull this up. Save image. PNG.
I'm gonna leave on my phone and join back on my computer, so just give me a second.
Okay.
All right.
Okay. Very quickly setting it up so I can record the thing. Window capture. Okay, window capture, we'll do that. Okay. Got photos. Oh, I gotta stream this. Oh, crap. That's kind of important. Oh, you're streaming it.
I'm still streaming the board. I finished.
I think
I'm
I
on
could
my
just pop
computer
up
now.
the image onto the board, actually. That might be the easiest way to do this.
What'd you say?
I think I could just paste the image onto the board. That probably is the easiest way to do this.
Yeah, go ahead. If you want to move around the screen, make sure you still have moderating on.
Yep, yep. Let's see, converting it to an image. Wow, that's tiny. I think it's probably still going to be legible if I just make it big, though, so that should be fine. Okay. So we have mass and spring. Down a little bit. Decompress length of 10 centimeters. Okay. When a 0.05 kilogram mass is attached, the spring extends to 15 centimeters at equilibrium. Frequency of vibration. Ooh, okay. Okay. So first things first. This is, you need to find your spring constant for this problem. Spring constant is, it's the stuff to cancel it out. It's, is the spring constant, is it visible on the formula sheet at all? I had to pull mine up.
Yeah, there should be. Yeah, let me pull it back up. I closed out everything, so give me a second.
Spring constant, spring constant, spring constant.
Well, you can find it because you know that when there's a mass on it, so you know what force it is because you know it's going to be kilograms times 10 for gravity, and you know how much it extends. So you know when some force is applied, the distance it extends, and it's just force times change in x change in x times the spring constant is equal to force applied. So you can reverse that to get the spring constant.
Okay, so you have. Sorry, say that again, but slowly.
Do you want to start off by talking about springs in general before tackling this problem? Because this one's a high-level problem, to be fair.
That's true, it's a high level. Okay. So, springs, if we go back to energy, spring energy is 1/2. Oh, quick, I'll just type it out.
No, just start with, force on a spring. Start there.
What's on a spring?
Okay, here, I'll show you. I'll show you what I mean.
Go ahead.
Can you cancel your moderation?
Yep. There you go.
I think my tablet is not cooperating. We're trying to refresh the page. Sorry, guys. Come on. Almost there.
So wait, this is wait, sorry, just to clarify, this is the only problem he gave you?
Yep.
What?
The entire.
Nice.
Yeah.
Alright.
So yeah, I think he. Okay. The first. So what we did was we spent one day on mass on spring, one day on pendulum. Both days we just derived the formulas for them, and then we did a lab on them.
What?
And that's that, and then we just did this. As far as I remember, that's all we did.
Okay, I'm gonna very quickly make a general recommendation, which kinda sucks, because it costs money, but there's a great website called Albert.io. I don't know if you've heard of it. I don't know if you used it last year, something like that, or if you've ever heard it before. But if you go to it, it's just Albert.io. It has a whole bunch of sample questions for every single AP class. And the important part is specifically they have AP Physics 1. And their questions are really good.
How much is it though?
I don't.
Yeah, that's the thing. It's kind of
$12
expensive.
per student per school year.
The thing is, I don't know if that's
I think
$12.
that's district pricing. Yeah.
50 students.
Yeah, that's district pricing. So what I can actually do though, is because sometimes the school gets the full subscriptions. I can talk to Miss Baker and see if she will let us use it. Because I know, like, for history they get the full subscription. So I'll talk to Miss Baker and see if we can just snag that from them.
So does that mean that we can just do it?
But yeah, no. If she lets us use it, yes. No, but like, yeah, regular is like $60 or something. Like it is really expensive. I mean, it's great, but it's really expensive. I will talk to Miss Baker. I'll email her actually as soon as we get off here, so I don't forget, and I will ask if there's any possibility we can get access to that. But anyway,
You know what we could do actually, is we could just pull from Albert's questions ourselves and go over them.
yeah, I know. Like if we only get one account, that'll be fine.
No,
Anyway.
like, because you can access them without having paid for them.
No, you can only access certain units.
I can access 6.1.
It'll only let you go so far, and it's not like you can refresh and like try it. You go from a separate one.
No, like you can't
it's-
answer them, but we can pick them and go over them.
If it lets you do that for all of them, then sure. But I vaguely remember it not letting you do that.
It just doesn't let you put in an answer and check if your answer's right, but we of course can go over it. Like you and I
Well,
can go over it.
I'll still email Miss Baker.
Yeah.
But,
That's still a good idea, because if we can get that, that'd be awesome. Because Albert is stupid good. Like, believe me, it is annoying when teachers assign it, but if you, instead of looking at it as an assignment that you have to complete as practice, it is such a good practice tool. Because their questions are all really well done. Okay.
Okay. Anyway, to this stuff. So, where's my marker? All right. So let's just review springs real quick to make sure we're on the same page. So imagine you have a spring. Looks like that. And here's a wall, so it's stuck to the wall. And then at the end of the spring, you have a box, right? And so this length right here is what we would call its uncompressed length. So let's just say this was 1 meter. So the formula, the main formula that you're going to need to know is that the magnitude of the the magnitude of the force provided by the spring is equal to negative the spring constant times the displacement from its uncompressed position. So just looking at it, if the spring was in its uncompressed position, what is the force exerted by the spring? Always.
I
Yes.
mean, if it's uncompressed, then is it exerting any force at all?
No, it's not. And that would tell you it's zero, because you can see if it's uncompressed, its displacement from uncompressed is zero, so it's not exerting any force at all. If we displace this object over here by negative 0.2 meters, and let's just say for the sake of it, spring constant is 3. Okay. So what is the force exerted by the spring on that box going to be?
Wait, so when it says negative K, alright, so just be positive 0.6?
Yes.
Oh my god, I did math. I'm so bad. So,
Sometimes I struggle with doing decimals in my head, but yes. So yes, it's going to be exerting 0.6 newtons of force in the positive direction. So that's the thing. If we push this cube, this way, right, the force of the spring is always going to be pushing it back. Likewise, if I said that instead we displace the cube, let me erase. If I said that we displace the cube 0.2 meters in this direction, then our force is going to be negative 0.6, because remember we have negative 3 times 0.2. And so the spring is going to be pulling us back with a certain amount of force. So does this make sense so far?
Is this new information?
Yes. That is a good question.
I'm not hearing a yes. Is this not new information?
I mean, okay, so we learned that the spring constant times displacement is the force of the spring.
Okay. Good.
Good enough.
Yeah.
Well, so the important thing to remember is just that a spring is always going to exert force so that it gets back to its uncompressed position. Also, as a notation thing, compressed is sort of a misnomer because even if it's extended past its uncompressed position, like if I pull it out, you would still consider that to be compressed as far as AP is concerned. So just be aware of that. And just any position other than its uncompressed position is considered compressed. So the other thing is, let's say we said this box was 2 kilograms. So let's look at the situation we drew.
Don't kill yourself, Nathan.
I just choked on pasta. Okay.
What pasta are you eating?
I had to guess it's
Oh, I
just
don't
like
think
spaghetti.
The one with the spirals? Like, I don't know how to answer that.
Rotini. Rotini.
Yeah. That. Okay. So, okay, we're gonna pretend that didn't happen. So, so we have this spring. The spring constant is 3, and we displace the cube, the 2 kilogram box, 0.2 meters to the right. So as soon as we release that cube, can anyone tell me what the acceleration would be, or how you would get the acceleration?
Okay. Oh wait, actually, I mean, I don't think you can get the acceleration. Maybe if you use energy, but acceleration is the constant, so.
You can find instantaneous acceleration. You can find the acceleration at that exact point.
Oh, instantaneous acceleration.
Yes.
Yes. Like as soon as I let it go, what is the acceleration going to be, assuming no friction?
Is there a formula for that?
There is sort of a formula for that, but you want to sort of break it down into other formulas. You could write out a longer formula to do it, but you can get one number first and then use that number to get acceleration. That's what I'll say.
Would you use like F equals ma or energy or something?
Yeah, exactly.
Mm-hmm. You're going to use F equals ma.
So we know that the force.
Oh right, I remember that.
Yeah. If we didn't remember that, there might be a problem.
Yeah. So if F equals ma is critical to everything.
I remember using that to find non-constant acceleration.
Alright, well that's good. That means that he at least did that, which is good.
We did a lot of Newton's law.
Well, that's good.
Alright, I should probably map it out. Okay, where the frick is my paper?
I just got here. What are we solving for?
Right now we're trying to solve for acceleration.
Instantaneous acceleration as you let go of the mass.
Yeah.
So it's displaced 0.2 meters to the right. The spring constant is 3, and it's 2 kilograms. So what would the instantaneous acceleration be as you let it go?
Alright, so
Any ideas? Or just at the very least, any ideas on what you would need to do to calculate the acceleration?
so it is already partially done. I know we just did a step just before this. I don't know. I don't think there's all the people here for it. Oh, Andrea?
What? Oh shit! Sorry.
No. Well, you're just unmuted. So.
Didn't mean to unmute.
Okay.
All right, that's fine. So, well, let's start with this. If you ignore spring for a second, if I have any object, what do I need to know You need to know two things about any object in order to know its acceleration. One is its mass. What is the other thing you need to know about an object in order to know its acceleration?
First, and you can find that using the spring force that we found.
Yes.
I
So
just got my
in-
paper in, right? Okay.
All right. You want another minute, everyone, or does anyone have an answer or a way to get the answer yet?
Is it?
See the displacement was again.
0.2 meters to the right in the positive direction. Spring constant is 3. The mass is 2 kilograms.
Mm-hmm.
Okay, wait. So when you're given the spring constant is 3, since the formula is negative k, would it be negative 3?
No.
Yes.
Well,
what
when you're
are you
plugging it in, it would be negative. It would be -3. But
It might not remain negative, if there's other negatives in the
Yeah.
problem. But as far as plugging it in, it is -3.
Alright. Thank you.
where is that formula on the AP Physics sheet?
Near pendulums. It's like left column there from the bottom.
Oh, okay, there it is.
Yeah,
It
but I
doesn't have
don't
it as
know if it's
negative.
correct.
It doesn't because it says magnitude of
Oh,
force
right,
is
right.
equal to. Yeah, they just expect you to intuitively know that it's inverse. But I mean, at the end of the day, it doesn't matter. Anyway, does anyone have an answer or a way to get the answer yet?
We can just work through it.
Okay, sure. So, like we said, for any object, there's two things you need to know its acceleration. You need its mass and its force. Were you gonna say something else?
No.
Okay. So we mentioned this earlier, but we need to start off by getting the force because we already know the mass of the object. It's 2 kilograms. So what we need to know is that the force is equal to negative the spring constant times change in x. And I'll take a moment to touch here on what Alan was saying. So the way that the AP formula sheet writes this equation is like this. If I can move the screen. They write it like that. So all that that's saying is it's saying the magnitude of force is equal to the spring constant times the magnitude of displacement. The reason why they put magnitudes and take out the negative is sort of beyond me, but they're sort of expecting you to know if the spring is compressed, in the left direction, then the force will be in the right direction, or if it was extended out in the right direction, then the force would be in the left direction. If you just keep the negative in there, that just sort of does that for you. Just be aware in the difference in the way it's written. It doesn't really mean much. It just means you have to keep track of the directions yourself if you use that second equation.
Oof.
Sometimes I just can't move the screen. All right, so we know the force, or we don't know the force. We know the spring constant, which is going to be 3. I'm putting.
Your mic is having some issues, Nathan.
Yeah. Is it better?
Yeah, better now.
Okay. So as we said earlier, this is going to be negative 0.6, if I'm not mistaken. Right, Alan? I'm not stupid.
Yeah, it'd be -0.6.
Okay. So does everyone understand how we got the force there?
Okay.
Does anyone not
I think a
understand
better
how we
one.
got
Yeah, I
the-
think a better way to say it is: does anyone not understand? Does anyone have a question?
Okay.
Okay,
So
I
now
just want
we
to say
know-
real quick. I think a good way to do this, unironically, is to have it so that if you unmute yourself, it's like raising your hand.
Yeah, sure.
It's
that's fine.
actually like not a bad idea, and I just thought of it.
All right, we will do that. But anyway, to continue. So now we know that the spring is essentially exerting a force on the cube this way that is 0.2 Wait, what did I say? 0.6 newtons that way, right? And I took out the negative because the negative implies direction, so I just added a direction, so I don't need to say it's negative anymore. So now we have a 2 kilogram object, and we know that if force on it is 0.6 newtons. So how can we get acceleration? Any guesses?
I mean, like it's F equals ma, right? So,
Mm-hmm.
if we have mass and we have the force, then we just divide the force by the mass, and we get the acceleration, assuming there's no other forces acting on it.
Yep. So if you assume all other forces are negligible, you'd get 0.6 is equal to 2 times a. You're going to do 0.6 over 2 to solve for that. And so your acceleration is going to be 0.3. And if you were to keep, if you were to draw out the units and do dimensional analysis on that one, you would see all the units work out. Or you could just, trust. So the instantaneous acceleration, as soon as I let go of the spring, is going to be 0.3 meters per second squared. Any questions about that? Okay. So just a couple conceptual things I want to point out about this, which will help you on the AP exam. Maybe, I don't know about this one, but it can help you speed through things. If you have a spring and it's extended, I'm going to draw my spring really stupidly because I don't care anymore. And so we have this, and it's extended this way by 0.5 meters. And then I let go, right? Obviously, we know it's going to have an acceleration as we just calculated. It's going to be different, but it would have some acceleration. It's going to move to the left, right? Assuming there's no other forces on the system and assuming no friction or anything like that, what will be its maximum displacement in this direction? Wild guesses are fine.
0.5.
Yes, 0.5. And that is because energy is conserved. So we said there's no other friction, there's no other forces. So if it were to go less than 0.5, energy would be lost somewhere. And that doesn't make sense. So it has to go all the way to 0.5. So a couple of other things to talk about. When it's at its maximum displacement, either when I immediately let go of it, if I just moved it there, or when it travels over here and reaches the end, what is its velocity always? The moment it gets to its maximum displacement.
What?
0?
Yes, 0.
Yes, 0.
What would be a good idea,
Because-
Nathan, is if you could probably graph the velocity versus time to show that relationship.
Sure, yep. So, in fact, we can make several graphs.
Yes.
So oops, that's not the right one. So this is a graph. So this is time, and that's velocity. So its velocity will start off at 0. It will reach a maximum, go back to 0, reach a negative maximum, and go back to 0. And I should extend that axis.
Okay, I have to ask. Did he draw a graph or something like this, where he did displacement, velocity, and acceleration?
Yeah, I did.
He did? Okay, good. Because that's... How many people remember that graph? How many people don't remember that graph?
Not me.
In order to remember it, they have to have
Paid attention when they were looking. Okay, fair enough. Okay, so if there's anything you take away from this review session at all, have it be these graphs. Seriously.
Yeah, this just understanding the general features of these graphs will help you, even if you don't know the math right away. You might at least be able to make good, educated guesses.
Right.
If you don't know this stuff, it's going to be a lot harder to look at the equations, and you're just going to be like, what do I do? So the next question is, so we said at its maximum displacements, the velocity is always going to be 0. So the next question I'm going to ask is when it's at its uncompressed displacement, right? What is its acceleration always?
Not numerically, just like concept. Like, don't give us a number. But
Well, there is a number there, but
I guess there's a number. Yeah. I had this the same
but what is its acceleration always when when the object is at its uncompressed position?
0.
Yes.
Oh.
Do you have any idea why?
Because it's uncompressed, so it doesn't have any reason to move.
Right. Well, there's no force, right? Remember we said when it's an uncompressed position, there's no force applied by the spring, and if there's no force applied by the spring, the acceleration has to be 0.
I'm gonna really quickly, Nathan. I'm gonna say that each node in we should probably label this graph in some way. Maybe maybe we say
Go
this is
ahead.
a sine graph or something like that. We just do pi pi over 2, pi 3 pi over 2, because that should be familiar for most people here. That should be.
You're
No.
saying that the x-axis? I don't think
Yeah.
that's. I mean, if you want to add it, go
Well,
ahead.
there
add
should
it
be
to-
some
that's right
way
there.
to keep them. Or do you want to draw the acceleration graph overlaid onto the velocity one with a different color?
No, I'm drawing them like right below each other, but where the axes are the same.
Oh, okay,
That's just
gotcha.
where I'm drawing them.
Okay, never mind then.
So like we said, the acceleration is going to, when it's at. So just to clarify here before I start drawing this, oops. So this is at its max in the positive direction. This is going to be at its uncompressed position. This is at its max in the negative direction, and this is again at its uncompressed position. So knowing that, we can say that when it's at its uncompressed position, acceleration is going to be 0.
Right?
Yes. The first graph is velocity.
This should be. Yeah.
Wait,
I
no,
did
I did
you
not.
didn't. No, this should be here.
Yeah, I'm stupid.
Alright, I got you. I can work on that if you want to keep moving on forward. I can just move it
Yeah,
over.
you fix that.
Yep. So we have max here. This is 0. Then you have this here. This is max. That's
Yeah, that
negative
one's max
x.
in the negative direction.
And then this is 0 again.
And then that loops back up to max.
If
in the
anything,
positive
actually, let me just draw another graph just really quick here. To kind of parallel that. It's max, 0, and then 0, and then back up. Okay, wait, hold on. It's 0,
direction. Finish up.
here, you have your max, down to, you scrolled it just as I was doing that. 0, max, 0, negative, 0. And then back up to max. And that's your x.
Okay, so what you'll see is that your acceleration graph, minus drawing abilities, mirrors your displacement graph. Does anyone have any idea why that is?
It should be the
The
opposite. shouldn't
acceleration isn't constant because the acceleration isn't constant because it's not a straight line in the displacement graph. Oh wait,
it? Also, I think
Never mind.
I think your acceleration should be.
Yeah, okay, so technically you are right, Alan. Yes, it should be negative. Hang on, let me...
Yeah.
I didn't realize you were going to draw the graph that way. How do I erase this? There we go. Let me just fix the nuance here. There we go. All right. Well, it's the same thing, but it's flipped on the y direction. So why are they? You can relate to the equations if you want. Why are the acceleration and displacement graphs inverses of each other?
Could you repeat the
So what-
question? Sorry, I didn't hear you.
Yeah. So why are and you can relate it to the equations if you want, but why are the displacement graphs? Alan, if you could draw change it next there. Yeah. Why is the displacement graph and the acceleration graph the same, just flipped on the y-axis?
I don't need we don't need relations to each other. If you think of how you define the displacement to the velocity, how they interact, and how the velocity interacts with the acceleration. Oh, we lost someone.
well, so in the velocity graph, it's getting, velocity increases and then decreases and then increases because it's spinning, but the acceleration graph, it gets, because it's not constantly accelerating, it still changes. That, I don't know.
All right.
So-
Well,
It is a very hard question. It's also a very hard question to ask, not just answer. But
Yeah.
the important thing to take away is that for your displacement here, your velocity is at 0 at the maximum displacement, and then it becomes positive, and then it changes to 0, and then it changes to negative. And the thing is here is that if you imagine it being repeated, not just starting at 0, and you watch as it continues. Let's say, for example, instead of looking at the beginning here, you look at like the middle. You look at this time where the velocity hits 0. If you look here on this graph, velocity is at 0, displacement is at its maximum negative, and acceleration is at its maximum positive. So if we imagine like this scenario in our head, what's happened is as it approaches its farthest displacement, it starts slowing down, and then it eventually stops. And at that moment when it stops, it's at its maximum displacement, your velocity is at 0. At that point, it will have slowed down as fast as it had been, because of course it increases in how much it slows down the further away it goes. And then it turns back around, so of course your velocity starts going negative, your displacement starts increasing, and your acceleration starts decreasing back down to 0 as well. And it's a cycle of that, of those things changing and affecting each other. This is kind of off topic, really quick. Who here is taking calculus right now? Because I know at least some people are. Okay, Michael, you are. Anyone else?
Yeah.
Okay, so we have Michael and Alan. I'm assuming that's it. Rashab is
Rich
too.
Bobby.
Okay. For you three specifically, have you guys dealt with derivatives of sine functions yet?
Yeah.
Okay. Can one of you happen to tell me exactly what this matches up to? Like what the x will be here?
Wait.
You may not have
Like,
noticed, but if you look at it, your displacement graph is a graph of
negative sign.
It's a the displacement is a
Wait.
cosine graph. Something. Hold on. Wait.
It's the velocity
Which
is
was
the
the-
derivative of the displacement.
Wait, which was the displacement? Which was the acceleration?
Acceleration is the a. Acceleration's here.
Okay. Oh.
Right. I mean, so I'm gonna be honest. I'm not. I don't think this is that helpful as to what we're talking about. But what I was trying to get at is velocity is the derivative of displacement, and acceleration is the derivative of the velocity, or the second derivative of displacement.
Right. And it's for people who aren't in calculus, it doesn't make sense. When you get to calculus, this makes understanding calculus so much easier. It's not even funny.
All right. Anyway, moving on to the things that do
That's
affect people not in calculus. What I was trying to get at with the question was sort of this. So what in our box? What is the one specific thing that affects acceleration in our scenario?
The spring.
What did you say? I couldn't hear you.
The spring.
Right, and so the force applied by the spring, right? So
Yeah.
the one thing that's affecting the box there is the force applied by the spring, the force exerted on the box. And what is the one thing that affects the force exerted on the box?
The mass.
Not exactly. Close though, but not really. It's going to be the displacement, right? If the box is not displaced, there's no force applied. If it's displaced a lot, there's a lot of force applied, right?
Yeah.
And remember, they're always in opposite directions. If you pull out the box to the right, the force applied is to the left, is pushing it back to the left. If you push the box into the left, then the force applied is going to be pushing it back out to the right. And that's why the two graphs are inverses of each other. Because as it gets displaced more outward, the force is pulling it back in, and therefore the acceleration is going back in. As the box goes closer and compresses the spring, the force on the box is pushing the spring on the box is pushing it back out, and therefore accelerating it back out. So that's why, whenever we see right here, when the displacement is at its maximum positive, its acceleration is maximum negative. When the displacement is 0, acceleration is 0. When displacement is max negative, acceleration is max positive.
Hey Nathan, we made another mistake.
What?
That's why my derivative thing didn't work. Velocity goes upside down. That's what
You
did
know-
it. That's why I was confused.
You know what? To be fair, okay, my graphs were right, your graphs were wrong,
Yeah,
and
no,
then
that's
I
because I was
adjusted my
following your
graph
labels.
to match your graph.
Your labels were wrong, and I followed your wrong labels, and I made a wrong graph. But now,
No. Okay, I originally drew my acceleration graph like this, right? These two
Yes.
graphs are correct, and if you drew the acceleration graph the other way, then they would all be correct. I'm just saying, I am
fix it real
just
quick.
saying
I'll
I
fix
was
it real
right.
quick. I'll fix it real quick. We're fine.
Anyway, despite me and Alan arguing here, yeah. So the other key thing to just remember is, when your displacement is at a maximum, right? The farthest out it gets. Your acceleration is also at a maximum, but in the opposite direction, but your velocity is 0. When your displacement is 0, when you're at the neutral position, then your acceleration is also 0, but your velocity is max, right? The fastest point you will ever be is when you're in the middle. And if you think about that, that sort of makes sense, right? As you get closer to the ends, you start getting pulled back, but when you're in the middle, you're going to be going the fastest you can possibly go. Do you have any questions about that so far?
So essentially, if I'm getting this right, is that if you start at the starting position, right? So let's say you pulled it down and then let it go, right?
Mhm.
As once you let it go, as it pushes back up to its normal position, is it accelerating or is it decelerating?
So, accelerating and decelerating in this context, you don't use those terms, because I would say accelerating upward or accelerating downward, because, like, for example, if you're talking about a vertical spring, and you pull the spring down and let it go, right? Once it reaches its, middle position, its origin position, it's going to technically start slowing down. But, as far as speed is concerned, but it's always been accelerating downward the moment it crosses that point. Even when it gets to the top and starts getting faster, it's still accelerating downward. So
okay.
Yeah. Here, I'm gonna use my mouse on this one just so you won't get the delay. I'm gonna just use sideways springs because when we use sideways springs, you don't have gravity involved, so we don't have to deal with that yet. But let's see, can I move this? Yes, I can. All right, cool. So, if I pulled this out and imagine the spring is following it, right? Or actually, even better, let me do it this way. Cool. I don't know what that line's doing there. That's fine. But now I can just do this. Okay, so imagine we have this and we pull it out this way, right? As soon as we let go, it's going to start moving this way, right? Obviously, the moment we let go, its velocity is 0 because it wasn't moving. But its acceleration is maximum because the force is maximum. So it's going to start accelerating in this direction, this way. And let's say that its neutral position, its uncompressed position is there. So here's the thing, though. As soon as it passes this point, right? So all the way from here to here, its acceleration is towards this position. So it's always to the left, right? The moment it gets here, its acceleration is now in the positive direction, or towards the right, towards this point, right? But it's going to get slower until it stops and has its maximum acceleration but 0 velocity, and then it's going to get faster going back towards the middle. But that entire time, it's accelerating to the right. So that's why I wouldn't say accelerating and decelerating, because
okay. So it's not really like so it's not accelerating and decelerating because it's not a matter of speed. It's just a matter of like which direction it's accelerating.
Yes.
So the velocity will change because it's accelerating the other way.
Yeah. So if I label this is the negative direction, this is the positive direction, right? Remember that acceleration is how fast velocity is changing. So as soon as I go this way, we're saying acceleration is positive, so it's some positive number. So we're saying velocity has to be getting more positive, right? So, but when we're going this way, our velocity is currently negative. So our velocity is going to get less and less negative until it hits 0, and then get more and more positive. That entire time, it's getting more positive because it went from, let's say a negative 30 to a positive 30. It's getting positive the entire time, but for some portion of that, exactly half of that time, it was negative, and for the other half of the time, it was positive. So even though it looks like, it went here and bounced back, the acceleration didn't change. Well, the acceleration didn't change directions, rather. The magnitude of acceleration did change because of the spring, but it was always accelerating in the positive direction, even when it changed when the velocity changed.
I just very quickly went into Desmos and graphed their graphs and put them on the same one, so it's easier to look at them. And have them.
Can you label them?
I've done my best with the colors. I guess the
Oh,
blue green doesn't
I
really
gotcha.
match.
All right, but yeah. So then when it's here, so over here it had a velocity of 0, right? So then from this whole point up until the middle, it's been accelerating in the positive direction. As soon as we hit middle, it's no longer accelerating. But it's had that whole period over here of accelerating, so its velocity is now going to be the maximum it can be. Because as soon as you pass here, what direction is it going to start accelerating? Can anyone tell me?
It's gonna start accelerating back left again.
Yep, back left and towards the negative direction. So as soon as it passes this point, its speed is going to start slowing down. So it gets here, and then it starts going back. And again, once it gets back here, it's going to be its maximum velocity, but in the negative direction. So that's, remember, so if you watch the spring here, as soon as I let go, maximum acceleration, maximum displacement, but opposite directions, because its displacement is maximum positive, its acceleration is maximum negative. Here is its maximum velocity, 0 acceleration. Here is 0 velocity, maximum negative displacement, but maximum positive acceleration. Back to 0 acceleration, maximum positive velocity, and then back to the beginning.
Mm-hmm.
Yeah, okay, I get that.
Yeah.
Any other questions so far about springs and the equation for it?
Yeah. It's a lot to take in.
Yeah, and especially you guys did waves first. Like, normally you would do this first, and yeah, it sounds a little more complicated, but it actually makes waves easier.
It
But,
does. Yeah.
But anyway, yeah, if no one has any questions about that, we can start talking about periods and frequencies and stuff.
Is there any chance you can... Actually, no, never mind. Yeah. Alright, that's good.
Okay,
Oh.
actually, scratch what I just said. We're going to do an energy first.
This real quick. But isn't
Yeah.
energy just the equation?
You need to do, potential and kinetic energy. That's all.
Yeah, we know how to do energy, I think.
I
Okay.
because yeah, they've already done spring energy. And energy
Yeah,
would
Wait,
just
they
change
did that
acceleration.
before simple harmonic motion? What?
Yeah.
We just learned swing energy with kinetic and potential energy.
Yeah.
Okay, so you know it's 1/2 k change in x squared, right?
Yeah.
Okay. And better question is, would you know if I gave you this scenario that we had up here, would you be able to calculate its maximum velocity? So that's the important part.
Okay, so the situation, like in the problem or in what you give, in the thing you made?
So just, I understand you're all saying you understand kinetic energy, and that's fine. I just want to make sure that we can apply it to what we just learned here. Like if I said that a spring box 2 kilograms, you can see I'm carrying less and less with my drawings here. And I said it was displaced, let's just say 0.5 meters in that direction, and spring constant is 3. So at some point it's going to reach its maximum velocity. Remind me again, when does it reach its maximum velocity? Like what displacement?
0, right?
Yep. So what if I give you these numbers? Can you tell me? Let me clarify. This is a 5. You don't have to calculate it. Just tell me how would you find it. What would its maximum displacement be? That is not amazing. Or not maximum displacement. Sorry, maximum velocity.
Well, would you use energy?
Yes. The only thing you use in this problem is energy.
Alright, so then it would be potential and kinetic, so that would be potential is just spring, so it would just be 1/2 k squared equals 1/2 mv squared plus 1/2 k squared. But different k.
The k's are the same. Well, no, 1/2 mv squared and then
Oh,
1/2
but-
kx squared.
Oh yes, yeah.
Yeah. So just so everyone we're on the same page, its potential energy. So you're pretty much going to be its. Can I draw? There we go. Its potential energy. Nope, that's IB notation. Or is it? Wait, is U AP or IB? I forget, Alan.
No, I think U is IB. I think
Anyone
potential
clarify that?
is PE.
Okay, sure.
The sheet
P-
uses you.
Oh really?
Okay, so she uses U. We're gonna use U. All right.
I don't
so
know
this
why.
is- It's just U is equal to potential energy is equal to kinetic energy, and potential energy is going to be nope, not today. All right, so U is equal to 1/2 the spring constant times change in displacement squared is equal to 1/2 mass times the velocity squared. You know, well, these two are going to cancel out, obviously. You know the mass, you know the spring constant, you know the displacement, and you need to find velocity, so you just solve.
Also, because it's like decompressed, you don't actually have to put because you're solving it for when the final is decompressed is at like equilibrium. You don't have to 1/2 k squared there.
Yeah, so since I'm asking you what is its maximum velocity, you know that when it's its maximum velocity, all of the energy from its displacement has to be going into its velocity, and therefore its displacement at that point is 0. So you only have to deal with taking all of its initial potential energy and converting it all into kinetic energy, because the point when it's will be at its maximum velocity is when all of its potential energy is kinetic energy. So you don't need to deal with x squared twice.
Alright.
Now, if you said something like when is its velocity when it's at some displacement, you have to calculate its initial potential energy to calculate its potential energy at that point. So same equation, subtract the two, and then put that into your kinetic energy equation. Does that make sense?
Yeah, that makes sense.
So I'm glossing over that just because you guys said you understood energy. So if you have any questions about that, please let me know.
Going
Any
once.
other questions?
Going twice. Okay.
Okay. Period time. All right, so the period equation is... Alan, would you like to read it off for me? Because I don't have this stuff memorized.
Period equation. Let me pull it up.
It's like, I think it's right column, one of the top ones.
One of the top ones.
It should say TS. It should be the
TS.
variable.
Okay, TS. We've got TS equals 2 pi and then in square roots m over k.
All right. So this is the
Little k, not big K.
Alan, I am drawing on a board here. Does it really make a difference?
Yes. That's the difference between kinetic energy and spring constant. Of course it makes a difference.
No, isn't it the difference?
That's fine.
Isn't it the difference between that and the charge constant?
That's not what it says on this sheet. I might just be wrong.
Anyway, that's irrelevant. Okay, so this is the equation for a period of a spring, or of any oscillating system like this. So one thing you should notice that's interesting is that displacement is not anywhere in this equation. And so what that means is if I have two springs like this, again, my drawings are getting worse and worse as we go on, and this box I extend all the way out here, and this box I extend just a little bit, and I let them go. They will have exactly the same period. They will go to they will reach their negative displacement at exactly the same time, and they'll reach their maximum positive displacement at exactly the same time. The only difference is the bottom one is going to move much faster than the top one, because it has to travel a much greater distance in the same time. But changing where you pulled it from does not change its period or its frequency, because remember, period is just 1 over frequency. Any questions about that?
I think this is another time to just bring down and put it right next to here. The image that we used earlier, that I got from Desmos earlier, because every single, it's out to the left, every single time you want to graph your displacement, velocity, and acceleration from this kind of motion, it will always look like that. Your blue will always be your velocity, your red will always be your displacement, and your green will always be your acceleration.
And which one's red? Which one's green?
Red is displacement and green is acceleration.
No, I mean which one do I?
Sorry?
I'm colorblind.
Oh, the one on the bottom. is the red one. You see the effect.
Thanks.
Let me see if there's a way I can easily mark that for you.
Should be able to draw.
No, it's good. I got it.
Okay. Well. Okay. So yeah, if we ever do that by mistake and just have colors and just let us know. Anyway. So yeah, this is the equation for a period of a spring. That's like about it. Like the only things they're gonna do with these two things is like give you a scenario of like a spring has a frequency of something hertz and it's a mass of something, and what is its spring constant, for example, right? Just and you guys said he didn't really give any practice problems for us to do besides that one that was posted earlier, right? Correct.
Yeah, that's like the only practice problem we really had.
Okay. Well, let's solve that one first, and then maybe I can conjure up some other ones.
I feel like another thing that's important to mention is that the structure, like what creates a wave, is that like motion, that repeated motion. But every single particle in the wave is slightly out of phase to the one before it and the one after it. So it's slightly forward in its like, in its cycle, or it's slightly forward in its cycle than the one behind it, and it's slightly behind it in its cycle than the one in front of it. So, and every single wave is like that. It's just the difference between a longitudinal and transverse is that longitudinal is, you take the spring, and it's moving back and forth like parallel to the ground, if you want to imagine it like that, and transverse is it's doing up and down.
Okay. So.
Do you want to do this one, or do you want me to do it?
I don't care. I can do it.
Right.
I haven't done a question like this in a long time, so I apologize in advance if I am rusty. Let me find where this is. I mean, this doesn't seem too bad, but maybe I'll do it and I'll be like, what the heck is this? All right. So this one is dealing with a vertical spring. Can I get the screen to move with me? There we go. All right. So this one is dealing with a vertical spring. So we have a spring, and it's like this. So with no mass on it, its decompressed length is going to be 10 centimeters, right? Or 0.1 meters. So then we're going to place on this a cube or something, some mass, that is 0.05 kilograms. I'm not going to draw that out, but just assume it's 0.05 kilograms. And when we do that, the spring extended to be 15 centimeters, which is an extra 0.05 meters, right? So this 0.05 meters here, and I'll just if I do anything wrong, just let me know. But that's going to be our change in x, because it was originally at 0.1 meters. And let me move so I can actually write this down. So that's our change in x, because it was originally at 0.1 meters, and then it added an extra 0.5 or 0.05 to get to 0.15 meters total, or 15 centimeters. So from that, we should, and we knew its mass, so from that we should be able to calculate the spring constant. So if we know that this thing here is 0.05 kilograms, can anyone tell me what force is that box exerting on the spring?
Uh, 0.05 times 9.8.
Yep, or just 10 in this case because it's easier.
Yeah. So, but
I don't know
0.5,
if he if on his test he requires you to do 9.8, but on, like we said before, on AP 10 is fine.
So 0.05 times 10 is just 0.5.
Mm-hmm.
Yep. So 0.5 newtons is being exerted by the box downward. And it said this was at equilibrium, so we know that the force exerted by the spring is 0.5 newtons upward because it's at equilibrium, nothing's moving. So we know that 0.5 newtons is equal to the spring constant time. I'm gonna have to move this over, aren't I? Let's try this. There we go. All right. So we can say that 0.5 newtons is equal to the spring constant times the change in x, which was 0.05 meters, right? And so we just solve for k, so we say k is equal to 0.5 over 0.05. So therefore k.
Important to note, we're using magnitudes of force and displacement here, because
Yes.
k is unit. It's not unit list, but it's designed to cancel. So its units don't. It will never be negative. K itself will never be negative.
All right. So so our spring constant is 10. So does everyone understand, or sorry, does anyone not understand how I got the spring constant there?
Going once. Going twice. Okay.
Okay. So now we have our spring constant. So let me see what the rest of the question asks. So it says, what is the frequency of vibration for this system? So remind me again, Alan, what the period equation is.
The equation is t subscript s, so period, is equal to 2 pi times the square root of m over k. And that's square root of m over k total, both of them.
Like that, right?
Yes.
Okay. So our period, is going to be 2 pi times the square root of the mass, which is going to be 0.05 over k, which is 10. And if we solve that out, that is going to be 2 pi times 0.7. And then the final frequency is going to be... Do you mind erasing the stuff that's below me, Alan?
Where's this below you? Sure.
Actually, I'll just move. Never mind, it's fine.
Can you move all that up easily?
No, I'm just going to keep moving to the right.
Okay.
Indefinitely. So it's going to be 0.44. So that is our period. The question, of course, asks for the frequency. So how do we get the frequency from period? Anyone?
1 over period.
Yep. So 1 over 0.44 is 2.25 hertz. Are there any questions about how I got the frequency? If anyone spots anything you think I did wrong, by the way, let me know. All right, going once, going twice. Cool. So the next one is, if the mass is pulled up to 20 centimeters and then released, what will the maximum speed be of the mass? So we just sort of talked about this a little bit ago. And this is pretty much entirely an energy question. So, and again, the only thing you need for both of these questions is K. You just need to know the spring constant. So we would pretty much say that its final energy, so its energy final is going to be 1/2 mv squared. Its initial potential energy, that's a U, not a V, just work with me, is going to be 1/2 k change in x squared. And we know what k is. K was 10. So 10, 1/2 10 times, what was it, Alan? 20 centimeters?
20, I think it was 20 centimeters. Hold on, let me check. It is... Oh, come on. Hold on. It is 20 centimeters, yeah.
Okay. So that's 0.2 meters. And that's all equal to 1/2 mv squared. Halves cancel out. Mass was 0.05, oops, 0.05 kilograms, which is going to be equal to 0.2 squared times 10, which is 0.4. I forgot to write v squared over here. Whoops. Sorry again. So then that ends up being v squared is equal to 0.4 over 0.05, which is 8. And then that means that the maximum velocity is going to be 2.8 meters per second. Does anyone have any questions about how we got that?
Nah, that's all. I just have like a quick question.
Mhm.
How different is the whole the whole pendulum harmonic motion thing? Like, is that too different from this one?
Okay, so we can go over that.
Because it's just like I don't know. Like it's been a while, and my brain is like slowly frying.
Mhm.
So I just feel
So-
like, can we just really quickly go over mass on the pendulum?
Yep. So the first thing to understand with mass on a pendulum, is that it's what we in the physics world like to call a lie. Sorry if you hear my cat in the background. The equation that is listed on the AP Physics sheet, which is the period of a pendulum is equal to 2. All right, hang on 1 second. All right, is equal to 2 pi square root of length over gravity. So this is an estimation. This only works, in the real world at least, for angles less than 50 or 15. Now they could give you a problem with angles greater than that, and you'd probably be expected to solve it using this equation. But if you ever did like a real world lab, you would notice that this equation does not hold true for angles above 15 degrees. And if you're curious as to why, we can talk about that later. But it's not super important. Besides the fact that it's a different equation, it is more or less the same. You would solve exactly the same problems with it. So, just like we did before with 2 pi m over k, instead you're just going to use the length of the pendulum here and gravity, which is 10. Then the other difference is, of course, kinetic and potential energy, where potential energy is going to be mgh, and kinetic energy is still 1/2 mv squared. So, like, I can make up a problem. If we have a pendulum, and it is 1 meter above its normal position. So its normal position would be like down here, and it's currently 1 meter above its normal position. What would its maximum velocity be when I let it go? Does anyone know how we would solve that?
So if you're looking for the velocity, and actually, I mean, could you just use like F equals ma for that?
That would get you acceleration. That's not going to get you velocity, though, unless you know calculus, which you don't need to
mgh
solve it
equals
using
1/2 mv squared.
Yep, correct. So it would be and you're right. I didn't give you the mass. This 1 kilogram for the sake of it. But yeah, mgh is equal to 1/2 mv squared. Your m's are going to cancel out, so it's going to be 1/2 v squared is equal to gh. Actually, you didn't need the mass. Oh, never mind. And you're just going to solve. Although in a real problem, they probably wouldn't give you this. They would probably say something like the angle here is 12 degrees or something. And that you're going to have to use, sine is equal to opposite over hypotenuse, for example, in order to solve for the height here. Does that make sense?
Yeah.
Okay. That's pretty much the only difference. You can get the force anywhere on it by sort of... Well, you guys haven't learned tension, have you?
Wait, so just to clarify, so if they do give you an angle, though, how do you factor that into the energy?
So if they give you an angle, you just need to find what this value is, right? So you pretty much just need to, you're going to need to use, what's the thing? Sine is equal to opposite over hypotenuse. So you would draw a triangle here, right? And, if you know that this is some angle, you can figure out the angle here. Then with using the law of sines and stuff, and you know that this line here is the same as this one here. So let's say it was 10, right? It was 10 here. So you use the sine of 90 minus 12, because remember this would be I'm sorry, the drawing's getting cluttered, but that's a 90-degree angle there. So it'll be the sine of 90, and Alan, correct me if I'm wrong anywhere in here. 90 minus 12 is equal to, let's say this is, I don't know, b is equal to b over 12, and then solve for b, and then this height over here is going to be the length of your string, so 10 minus whatever b ended up being. So the only difference in that, if they give you an angle as opposed to just the height to begin with, is you just have to find the height first, and then you continue solving it as we have been.
Alright. I think that's all I want to check out for today. So thank you guys so much. I'm going to head out now.
Yep, no problem.
Problem, man.
Does anyone else have any questions about anything you wanted to go over?
Nope, thanks.
No problem, man. Alright. Rashab, Lana?
I think the one thing is like, so, you know how waves are like, why do like people use pi to when talking about, like, I don't know how to explain my question.
Why would you use pi when talking about waves, basically?
Yeah, exactly.
So, what math are you in first?
I'm in Algebra 2 right now.
Algebra 2, okay.
Yeah.
Have you learned about sine and cosine in general?
Yeah.
Okay. I mean, the short answer is pretty much that it makes numbers easy. Like,
Okay.
that's pretty much the answer. Because, like, if you draw out, a graph, sine, like this, if that's 0, that's pi, that's 2 pi, always. Excuse my 2 there. That's pretty much the reason. It just makes the numbers easy.
Alright, that makes sense. And I think that's it, yeah. Thanks so much. I really appreciate it. You helped me a lot.
Yeah. No problem.
No problem.
Glad to help.
Okay, so.
The dipping of people as they're like, I'm good.
Alright, stop the recording now.